Well, you all know me because I've been around for a while, so I'm going to get into this right away. You all received the topics sheet that I circulated last week together with a reading list. Let's just briefly go over the topics before getting into more details. So the first part of the seminar, which I hope to cover today, will go over some very, very basic material. I just want to be able to talk at least up to concepts relating to bulk acoustic waves and talk about issues like polarization and degeneracies and things like that without getting into too much technical detail. What I like to do as I approach the tail end of this is bring in a notation and an approach which my students and I have developed over a number of years, which I think facilitates handling bulk wave, surface wave problems, and in particular multi-layered problems, and we'll get to that eventually. And this is what I call the matrix formulation. We have to talk about guided waves, and of course we only have guiding if there are some discontinuity somewhere. You know, waveguides have walls, surface acoustic wave devices have interfaces, free surfaces, and so the guiding is the result of some kind of boundary condition. And usually you don't know a priori what is the velocity of the guided wave until you have satisfied all the boundary conditions, and then when you find that that's all done, you have popped out what is the right velocity for the wave. Now the simplest guided waves are plates because they have two boundaries, like an electromagnetic waveguide. Surface wave is a little more complicated. It only has one boundary. It has a peculiar transverse field distribution and is not as simple even as a plate wave, but I will not be spending that much time on plate waves. In addition to these sort of very primitive concepts, we have the issue of what types of waves can exist. Now these are determined by a number of different factors, primarily the material that you're propagating your wave in and the propagation direction with respect to the crystalline structure of the material. That will determine the kind of waves you can have. But broadly speaking, there are just really three kinds. There's a generalized kind in which the polarization can be arbitrary, and usually is arbitrary. There are kinds of waves in which the polarization is in what I call the sagittal plane, and I'll explain this concept a little bit later. And then there are shear horizontal solutions. Now if we think of the top of this monitor as a free surface, and we have the normal in blue and the direction of propagation in green, then the plane formed by these two is what we call the sagittal plane. So sagittally polarized waves are those which have their particle field components, the displacement fields, in this plane. The shear horizontal ones are those that are perpendicular to this plane. So that's sort of the underlying situation. In general, your particle polarization can be anywhere, and that's what I call a generalized wave. And this applies whether we are talking about surface waves, plate modes. Any of these will have these features. And of course, when you get to layered structures, things can become very complicated, especially when you're layering materials that have different crystal symmetries. You find that sometimes unexpected results come up. And as I said, one of the things which determines what kind of solutions are allowed is frequently determined by crystal symmetry. What is the material? What type of a crystal symmetry does it have? and how are the crystalline axes oriented with respect to the propagation direction, that will determine frequently what are the allowed kinds of waves that you can have. Now, in terms of, excuse me, in terms of the type of solutions, more or less up to now, people have talked only about what we call non-leaky waves, no loss, a true guided wave with no attenuation. And this is what we've called the surface wave up to now. More recently, like perhaps within the last 5 or 10 years, many people have started working with another class of solution, which are called pseudo surface waves or leaky waves. Now, I'll go into details about what is special about those. Nevertheless, they have come in the last 5 to 10 years, and they're characterized by having a somewhat higher phase velocity. And as a result, since there is an inverse relationship between velocity and wavelength, this means that you have bigger wavelengths, and so your geometrical design, fabrication design for devices allows you to operate at higher frequencies. Very, very recently, there is evidence, both experimental and theoretical evidence, of the existence of a high velocity pseudo surface wave, and I will talk about that a little bit later on. These waves can be a factor of 2 to 2.5 times the normal Rayleigh wave velocity, just as the pseudo surface wave or leaky wave, which is the one line up, can be about a factor of 50% higher, rarely much faster than that. Now, all of these have their own use, and what's very important is it turns out that these waves are leaky in the sense that they do radiate some energy or some power into the bulk of the material. However, there are certain orientations and certain conditions which arise where the amount of loss is extremely small, and so they become practical in device fabrication. And this is what has given the impetus to using these waves more recently. Things, of course, get complicated when you have layers, and I will be spending some time talking about layers, and it is in the context of layers that I think the matrix formulation is the most powerful one, because if you use this method, then no matter how many layers you have, your boundary condition constraint is only determined by the uppermost layer, and so you never increase the dimensionality of the problem you're solving with respect to a surface wave or a multi-layered structure. So that I think is an important feature, and one that we have to take pretty seriously. Let's now move on to the next thing, which I call acoustoelectric waves. We're all interested in devices. We're all interested in using these as filters and other devices in the electrical engineering applications, in the telecommunications applications. So it's important that we can access these waves through electrical signals. And so this requires that we use piezoelectric materials, and it's only in piezoelectric materials that we have acoustoelectric waves. It's a general word used to signify the fact that the waves contain not only acoustic but electric field components. Okay, and we'll come to that again in more detail later on. By the way, since we're relatively few, I'd like to be as informal as possible, so if any of you do have any questions, please just raise your hand and we'll see how we can handle it. A thing which is very important with respect to the acoustoelectric waves, in the sense that these are sound waves, the electric field components which are part of this wave are propagating with the velocity of sound. We don't have an electromagnetic velocity. Everything, it's one wave, it's a unity, and it propagates with a specific velocity, and it's very close to the velocity of sound. So that the electrical problem is really an electrostatic problem in these devices. There are about 5 orders of magnitude difference between the velocities of sound of the order of, say, let's say 10 kilometers per second with respect to the velocity of light, which is about 10 to the 5 times higher. So they do propagate at the velocity of sound, and their properties really depend on very fundamental equations of motion, which are known as the electromechanical equations of motion. They depend on the thermodynamic relations between some of the field variables in the material, known as the constitutive relations. You're all familiar with the relationship between electric displacement and electric field through a permittivity. This is a constitutive relation. Hooke's law is a constitutive relation. It relates two types of variables in a material together. So in addition to the dynamic equations of motion, we have to satisfy the constitutive relations that that material has with its appropriate thermodynamic constants pertinent to its own crystalline symmetry and things like that. So these are very important, and you have to know a little bit about them. You don't have to know everything about them. Anisotropy is critical in a lot of the things we're going to be talking about. The orientation that you have selected for propagating your wave will determine a lot of its properties. And these are things I will come back to again and again. And unfortunately, these things are dependent on temperature, which is a problem that device designers have to face. So all these are factors pertaining to what we call acoustoelectric waves, and they're things that are going to come into some of the words and some of the concepts I'm going to be talking about. Now comes the question regarding, have you done your homework? And I'm going to assume that the answer is maybe. You got some sheets handed out in the previous, from last week, which are extracts from old. And if you go to what is equation 1.48, we have what is called the strain-displacement relation. This expresses the relationship between the strain in the material, the fractional elongations and so on, and the particle displacements. And it's a very innocent-looking equation. The quantity S, which is in that equation, is actually a tensor. It's, in this case, a 9-element 3x3 matrix. And because of symmetry requirements, and I'm not going to try and prove anything here, I'm just going to say this is the way it is and this is how we use it. Because of symmetry of this array, there are only 6 independent elements. You might want to make a note there about that, by virtue of being symmetric. Now, one of the things that we have done way in the past is to simplify the notation from a double index notation to a single index notation. Since we only have 6 independent quantities, let's give them 6 labels, and this brings us to equation 150, which, when you look at 149, you'll see that we have S1 through S6. These are independent ones, and there are factors of 2 that go into their definitions, which again are for convenience and nothing to really be particularly concerned about. So there are technicalities which are not really important in what we are talking about today. So we have 6 strains, and they are related through this equation to the displacements. This upside down symbol is a gradient type of operator. It's a derivative, and if you look at a little bit later on, you will find another relationship which expands these 6 components and shows you how they're related to the 3 particle displacement field components. So the little u's, which are on the right-hand side over here, are the displacement components, the actual particle displacements, how they're moving. This differential operator allows you to write the relationship between the strains and the displacement in this relatively simple way. It's a 6x3 differential operator, and it is referred to as the symmetrical delta sub s, okay? You can put it in a component form this way, but that's not really all that critical. Let me take a look at this operator a little more closely. And so here we are. That's just this thing repeated down here. And think about this. Okay, this is a 6x3 differential operator operating on 3 components of displacement. And let's ask some questions. Suppose I'm dealing with a bulk wave propagating in the z direction. Which of these derivatives are 0? And which are not 0? What's a bulk wave? A bulk wave is an infinite plane wave. It has no variation whatsoever transverse to the direction of propagation. So if we're talking about a z propagating wave, d by dx and d by dy disappear. Okay? And so what does this look like then under these conditions? Well, if you just take a look at this and you throw everything out except this, and that, then you can rewrite this in a very simple way. And this 6-component vector is just d by dz, which is the only non-zero derivative left over, of a bunch of numbers. And if you just write it out carefully, you'll find that there's 2 zeros and a 0 there, and easy. So that's how things simplify when you are dealing with a z propagating situation. Now, are there any questions here? Okay, so we'll proceed. The next most important relationship is the translational equation of motion. This you'll find in chapter 2, equation 222. And it simply says that this del dot t, which is another operator, defined in a calculus type of limit here, can be written this way. It's really a gradient operation, or divergence-like. It's d by dx of a vector t sub x, which has components txx, tyx, and tzx, plus d by dy of a vector t sub y, which has components txy, tyy, tzy, and d by dz of a vector t sub z, which has components txz, yz, zz. So we can either write this in this way or in that way. And the translational equation of motion says that this is the mass per unit volume times the acceleration. Right? This is a force equals mass times acceleration statement. So the right-hand side of this equation is the density, mass per unit volume, times the second derivative of the displacement, which is the acceleration. This is known as the translational equation of motion, and we can write it, if we call the vector of displacements u bar, we can write it in the way shown at the bottom here. And now I ask the question again. If we are dealing with z propagation only, and only bulk waves, the only non-zero derivative is d by dz. And so that vanishes, and we're only left with the rightmost term in 222. Well, let's show what this is going to look like. I'm going to do two things. I'm going to just pull the single non-zero term from here, and instead of writing rho u double dot, or d2 by dt squared, I'm only going to consider wave propagation now, sinusoidal wave propagation. So d by dt is replaced by j omega. And so the velocity field, du by dt, is just j omega u. So here we have these words of wisdom. D by dt is j omega. Everybody here should be familiar with that. And the velocity is the time derivative of displacement, and in the sinusoidal steady state it's just j omega. So this translational equation of motion can be written in the boxed form, and it's just the derivative with respect to z of the stress. Oh, by the way, big T is a stress. Okay, I forgot to say that. And is equal to j omega rho times the velocity. What's important here is that this is a first order differential equation. It's a matrix differential equation. Nevertheless, it's a first order differential equation, and is a very important component in what I will be saying a little further on. There is, by the way, in this context, a similar operator to the one I showed. Can I clear this one off now? Yeah, okay. There's a similar, we can say a similar thing to what I had earlier regarding the strains. Del dot T is a 6-component symmetric matrix with txx, txy, txz, etc., etc. This can be written in this way if we use the definitions shown by these circles, which is similar to the one we looked at just a little while ago for the strains. So the stresses also can be indexed as a 6-component vector. So we've done two things to simplify the story. The strains are reduced to a 6-component vector. The stresses are reduced to a 6-component vector. And of course, the particle displacement or velocity is a 3-component vector. And the relationship between those 6 and 3s is via this kind of an operator. And let me again come back to what we just had a moment ago, that the translational equation of motion ends up being d by dz of only these fellows, T5, T4, T3, because all the other derivatives vanish if we're dealing with a bulk wave which is propagating in the z direction. Okay? Now we can rewrite this equation of motion as d by dz of the vector t sub z, which has T5, T4, and T3 as its elements, and on the right-hand side, j omega rho v. Sorry? You
look in your monitor.
Oh, yes, I should look in my monitor. Yeah, okay, sorry about that. This, of course, is the same first-order differential equation that I had on the previous sheet, but arrived at, if you want, slightly differently. Nevertheless, there's our situation that we have. Now, what happens with a guided wave? If we don't have a bulk wave, let's say we're worrying about a surface wave propagating on this surface, and this is the normal to the surface. It cannot have an infinite extent in a direction perpendicular to the direction of propagation. And if it's moving that way, and this is the normal, then then these directions are infinite in effect. The surface is infinite over there. The only direction in which there is a boundary is in the z, normal to the z direction. Okay? Now here we'd be propagating, let's say, in the x1 direction, and the normal would be the z direction. The only zero derivative in these matrices will be the dy, the y component. So the moment we have a guided wave, we no longer have a simple first-order differential equation. The method I will try to develop and demonstrate and discuss later on shows you how, under those circumstances, one can still formulate a first-order differential system. If you're able to formulate something as a first-order differential system, then I suspect most of you are familiar with this. Anyone ever seen this before? Who has not seen this before? I've written x dot equals ax. Linear systems theory? Okay. Now we are going to get a statement for the acoustic problem, which is of this form, except that where in systems theory the dot is a time derivative, in our context it's going to be a spatial derivative. And we'll come to that a little bit later. So the point I want to make here, I'll be with you in a second. The point I want to make here is that the moment you have guiding, you have two non-zero derivatives. Yes, Majid?
That would be analogy to systems. You have AX plus dU.
Yeah. This is a zero force, unforced problem, yeah. See, when you're solving for the modes of a guide, you're looking at an unforced problem, okay? The excitation problem is something else, and you need some kind of a convolutional integration or Green's function calculation. Yeah. But for a free propagating problem, it's a zero input problem. Nevertheless, I would like to refresh your minds that the solution to this problem is of this form. Whoops. Where this is the state transition matrix, for those of you who are familiar with system theory. We will have a very similar structure when we start talking a little bit in a little more detail about guided problems. Any questions on this up to now? And we have then the basis for looking at problems, and my thrust is that we will be looking at problems in the context of first-order differential equation systems. The big advantage of this, of course, is that there's an enormous body of work, algorithms, computational software that exists and has been developed, which is based on the linear algebra and first-order differential systems. So let's take a look then about what kind of things do we expect from bulk acoustic waves. We talk about waves in unbounded media, so there's no spatial variation except in the direction of propagation, and here we have a phase progression. Okay, so for a Z propagating wave, we will have this is the Z dependence. Okay, if it's a wave, that's how it must be. Remember, we're using an e to the plus j omega t time dependence, the normal choice in electrical engineering. If you're used to the other way around, then you've got to put a plus sign here. So this is basically how our wave propagates. Okay, I've written it here for a Z propagating wave. On the transparency for which you have a copy, it's written for an X propagating wave. And as long as the direction is defined for the wave propagation, then this is defined. Now, what is different between guided wave problems and bulk wave problems is that there are explicit solutions for bulk wave propagation. You can calculate numbers for the phase velocities of your bulk waves, and there are 3 solutions. Remember the equations we had there? We had 3 variables relating 3 other variables. It's really a third-order system in a sense, and there are 3 solutions to the velocity of propagation along any chosen direction. Because the coefficients of these equations are real, these velocities are real, and the eigenvectors of the structure are orthogonal. So we have 3 solutions, mutually orthogonal. In an arbitrary direction, there will be 3 different numbers. For some orientations and some materials, you will get degeneracies, where you will have, for example, the commonest one is having 2 shear velocities exactly equal. So if we're dealing with propagation in this direction, then there's a shear velocity with polarization that way, which has the same velocity as a shear wave with polarization this way. And then there will be a longitudinal wave with polarization along the direction of propagation. Now, it's only in certain special cases that they simplify and break out in this simple way. Usually we have a quasi-longitudinal because we have a dominantly propagation direction component and two quasi-shear. Okay, and of course in devices it's frequently important to select directions where we do have purer modes preferably, and so this case is of special importance. Yeah?
If you have a crystal where you have quasi-shear and quasi-longitudinal, what does it mean to say that they're orthogonal? If you have some motion, relative to the crystal in 3 axes, you have motion.
It says that if we're propagating that way, okay, that the two polarization solutions, whatever they may be with respect to the direction of propagation, are still 90 degrees apart, spatially 90 degrees. So you can always rotate an XYZ rectangular coordinate system to line up with the 3 resultant polarizations. That's probably a better way of thinking of it. Anyone? Okay, so let's take a look then and bring back and recapitulate what we had earlier. Let's take the situation of z propagation. So the only non-zero derivative is d by dz. And as we looked on an earlier transparency, we have 5 non-zero components of strain related to the displacement vector given by this relationship. And since I'm going to work in stresses and velocities, I'm going to multiply by j omega, left and right hand side, and say that j omega times this is equal to dv dz. Okay, because I want to use velocity rather than particle displacement as one of my field variables. It's just a personal choice. It's not necessarily. You can do it another way. The translational equation of motion that we had was the derivative with respect to z of those 3 stress components, and that was j omega rho v. This was what I call the translational equation of motion. It's really the force equals mass times acceleration. Okay, stress being force per unit area, the mass is the mass per unit volume. It's a density. So we have these two. Unfortunately, we have 3 variables here, 3 variables there, and 3 variables there. So we've got to get rid of something, and this is where the constitutive equation comes in, the equation of elasticity, which gives us a relationship between the strains and the stresses. This is also known as Hooke's law, and the relationship between the 6 stresses and the 6 strains is through a 6 by 6 matrix, which is called the stiffness matrix. This is made up, its elements are elastic moduli. There are longitudinal moduli, transverse moduli. This is the thermodynamic description which relates the relationship between the stresses and the strains. So this is a thermodynamic quantity. Now, the relationship between, remember that S1, S2, and S6 were 0, just going back one way, and if that is so, then only 3 of these are non-zero, and so we can pull out those 3, and they will be related by a 3 by 3 matrix, which I call gamma 3, 3. superscript 3,3, made up of a subset of the elements that going into here. Well, let's look at that a little bit more closely. This gamma 3,3 relates T5, T4, and T3 to S5, S4, and S3. So when you look up in your stiffness matrix, you'll find that sorry, I got to come up a bit. You'll find that the ones you need, the second index pertains to the stress label. The first index pertains to the strain label. So T5 will be related to these through these 9 elements. Now, because this is symmetric, there are only, again, 6 of these are independent. But that's not something to worry about. The important thing is that only 3 strains are non-zero, and so I can express the 3 stresses that I'm looking for as the proper linear combination of these strains. Well, all this allows me to do is to eliminate the strain from this relationship up here, and so rewrite this top equation slightly differently. If we just multiply this by gamma 3,3, multiply this by gamma 3,3, that's going to be T5, T4, and T3, which is what I have over here. And the right-hand side I also multiply by gamma 3,3, so that comes down here. We now have 2 relationships in the boxes. And I think these are from the bulk wave point of view, these are the important things to look at, because I now have a first-order differential equation relating the stresses to the velocity, and another equation relating the stresses to the velocity. So I now have enough, I have reduced my problem to as many statements as variables, okay? This is 3 variables here, and 3 variables here is 6. I have the same 3 variables here and here of 6. And these are 3 equations and 3 equations. So I have the right number of equations for the number of variables I'm looking at. Now, perhaps this was a little quick. So if any of you have any questions on this, maybe we can take them.
You have 3 equations and 3 unknowns now? 6 equations.
No, I have 6 equations and 6 unknowns.
And the 6 unknowns are?
Yeah. The 6 unknowns are the 3 stresses, T5, T4, T3, and the 6 velocities, Vx, Vy, Vz. Okay?
Are they coupled, the differential equations?
Are they coupled? Well, since they are 2 equations in the same sets of variables, in a sense they are coupled. However, they are independent statements. Okay? One of them, this one here, strictly comes from the translational equation of motion. This one here comes from the strain displacement relation, and in between the 2 I've eliminated strain using the constitutive relation. Okay. So they are 6 independent statements. There is no extra stuff there. Well, let me talk about if I collect these two together, okay, and I let I have dt dz is equal to something. In fact, let me write these down again. That's one of them. And the other one, I'm going to write it this way. And this, because it's going to come up repeatedly, I'm going to give the symbol, the matrix symbol x, for the inverse of gamma 3, 3. Gamma 3, 3, by the way, can never be singular, so it's a well-behaved matrix. It does have an inverse, and so here are 3 equations in 6 unknowns, 3 equations in 6 unknowns, and if I just put them together the way which is at the very top of this transparency, I'll take this 3-component vector and this 3-component vector as one 6-component vector, and the right-hand side, this one only depends on the v, so we have a null matrix here, and then a row times an identity I3 matrix times v. So that first row of this dtz by dz equals j omega rho v is in there, and the other equation d by dz of v equals j omega inverse gamma 3 3 times t plus nothing times v. So this can be looked at as a 6-component vector tau, and that's what I've written at the very top of the let's slide this down so you can all see how it's been put together. And what is critical here is that this is the first order differential system in 6 variables, just like that. The same structure. The fact that there's a j omega there is irrelevant. We have a first derivative is some matrix times the vector itself. The derivative of the vector, this is in a time domain, whereas the green thing is in the space domain. But it's the same kind of algebra, it's the same kind of mathematics, and so I can write it in this form. Now, there are these 2 equations, by the way. I will recap them. Let me unzoom. Okay. We look at it this way. That's the first of these next equations, which I'm entitling the transmission line equations. How many of you have done transmission line theory? Okay. These are like transmission line equations. You have a spatial derivative is j omega times another variable. What is the transmission line equation corresponding to this? That look familiar? The voltage drop is proportional to current, and the other equation we have is of course here we have a scalar. Voltage and currents are scalars, but the algebra of this statement here is exactly the same as that one there. By the way, the sign here is not relevant. If you're concerned about the sign, the stress actually is the negative of the force. And so if you want to use force instead, your minus sign comes back in. Now, the phase velocity here in the transmission line, 1 over root LC. You may or may not recall this, but that's what it is. And if you see on my transparency, the phase velocity is 1 over root rho x. It's got the same algebraic structure, but you have to be careful now because now x is a matrix. Okay, and I'll come to that in just a moment. So what I wanted to put in perspective this afternoon was the fact that the equations of motion that describe mechanical waves, and in particular bulk waves, are virtually identical to transmission line equations, except that we're dealing with a vector statement as against a scalar statement. So you can think of these as 3 coupled transmission lines. Okay, it's time to talk about the bulk velocity. And so
We've got about 2 minutes.
I've got 2 minutes to go. Okay. If we talk about bulk velocity, then a priori we are saying that we have a z dependence which is of this form. Well, if you put that in here, the j omegas will disappear, and you'll be left with t sub z is minus rho phase velocity times the velocity vector. This coefficient rho v is the mechanical impedance of the material. You may have come across that concept before. Finding the velocities is equivalent to finding the eigenvalues of this matrix 1 over rho x, or the root of the eigenvalues of the matrix 1 over rho x, or gamma 3 over rho. This is just a simple problem. You just calculate the eigenvalues either of this matrix and you take the square roots, or you do a matrix square root and take the eigenvalues. Okay, depending on what kind of software you have or what you're prepared to do, one is easy or not. So let's then finish off today with some numbers which I which I will pull out. I think we'll have to get rid of it. If you take, for example, diamond, which is electric, and you calculate this gamma 33, don't worry about the numbers, just take a look here. It turns out that this is diagonal. You also see that the 4 position is just on its own. It's completely uncoupled, and that's just a statement that the electrical behavior is uncoupled to the mechanical, because diamond is not piezoelectric. When you do the eigenvalues of the square root of G33 over rho, as I said, and the eigenvectors at the same time, this is a command that MATLAB allows you to generate in one shot. You find the velocities are 12.8, these are in kilometers per second, and that one is polarized in the x1 direction. So it is a shear wave, because we are looking for propagation in the z direction. This one has the same velocity, is polarized in the y direction. It's the other shear wave. And this one is the longitudinal one, polarized in the x3 direction, and that's its velocity. Okay. And just to finish off, if we take a look at a piezoelectric material, and I just took a lithium niobate example, doing the same thing, you find that the velocities, again in the same units, I'll go from right to left, there's 3.57, we again have degeneracy, and you can see from the polarization, this is pure shear. Polarization, this is pure shear. If we take a look at the longitudinal velocity, it's significantly higher, of course, but if you look at the polarization, it also has an electrical potential component. I snuck in the piezoelectric effect while you weren't looking. Okay. So I think that's enough for today. So we'll pick things up next time, and
What shall we read?
What shall you read? For next time,